Okay, so good morning, and as we all know, we are coming close to the end of this fascinating 5-day session. And today it was kind of a little bit of change at the last moment that we had to do because of some issues. So I will be giving the first lecture today, and today's talk will be very less of physics, a bit of technicalities. I mean, we would like to ask this question that how can we make effective use of these effective operators that we have dealt with so far. And I will give you a glimpse of that. Of course, I mean, it's not a complete description, but there are more that one can do, and I will explain as I go along. Okay, so so this is the question: what do I do with these EFT operators that I am studying? Well, depending on your physics interest, you can study Higgs physics, say for example, or you can study dark matter physics with them. You can apply them to the neutrino physics. You can in general study collider observables and the contributions to the signals, etc. And in all these cases, a numerical implementation of these operators is often very helpful. There is a slight warning that it is not always necessary that, for example, if you just want to study the cosmological evolution via Boltzmann equations, you just need to compute the annihilation cross sections of the dark matters. It is not strictly necessary, but you never know that whenever you are calculating something, there might be some errors or mistakes that you might be doing in the process of doing those numerical calculations. On the contrary, if you successfully embed an EFT operator in some of these numerical tools that we will be talking on, you can actually be sure of some of the basic ingredients with which these EFT operators are constructed and its further calculation, like for example gauge invariance, which we have been all talking about, that can be checked thoroughly and etc., which while doing by hand or using by Mathematica and putting that expression over there to calculate the numerical outcome might give you something wrong. So it's better that you actually put these operators in this numerical tool, check their consistency, calculate their cross sections, and then you match to your analytical calculations what you are doing. Okay, all right. So this is just a glimpse of the landscape of numerical simulations that one can do. So this is the part which we will be mostly talking about, that getting the operators embedded in fine rules, which will help you generate the Feynman rules and the vertices associated with them. And then there are other packages also which you can use. For example, LANHEP is easier and it is more useful for dark matter related calculations. SARA is often helpful to kind of do this renormalization group running and so on and so forth. I will mostly talk about how does the fine rules actually look like. Then there are certain files that you can generate with these fine rules, which has all this set of particles, the vertices, their properties, parameters, etc., which you can then feed into some matrix element event generation like MATGraph, CalCAPE or Sherpa. CalCAPE was the one that we actually all started with. It was, I think, one of the oldest software which calculates all these cross sections numerically. MATGraph is the most modern one that you can actually use. And then there are showering hadronization that you can do using Pythia, and that is almost embedded in this MATGraph tool. And what thing MATGraph does that CalCAPE cannot? There is a simple answer to that, that whenever you have 4-body final states, say for example, you are producing, say for example, ZH. and you want to also have the Z going to L plus L minus, H going to BB bar, and so on and so forth. So whenever you want to calculate, say for example, 4-body final state, I mean using ZH, that is a trivial example, but you can have a new physics example, say a heavy quark which is depending to a light quark and a Z boson and so on and so forth. Calcade can still do that, but the problem is it takes enormous amount of time. So that's one. Whenever you have a large final state, then Calcade 2 going to 2, it's very easy, but to NLO calculations, I'm not sure if Calcade can do.
Can provide effective
vertices.
It can just calculate, but it cannot do NLO.
Yeah. So NLO calculations also, for example, you cannot do.
One point to add is that Sherpa does its own part on sharding.
Oh, Sherpa has this own part on sharding program. Also in MATGraph, as far as I know, that you can calculate the cross section in different ways. One is the usual trace technology, and the other is actually using helicity amplitude technique. I think MATGraph does using helicity amplitude, so this is very faster. Whereas Calcade does it using the trace technology, so that matrix element squared, etc. So therefore, it is the helicity amplitude you can produce. Yeah, exactly. So so then the part on showering and hadronization you can do using here, and then if you are interested in more sophisticated event generation, you can do this detector level simulations using Delphis and okay, I think this arrow is a kind of a mistake. So for example, you are interested in dark matter physics, like calculating the relic densities, the direct search prospects of these effective operators, then I think it is directly from fine rules that you can go feed files which are compatible with micro omegas. Actually, this is same software of Calcade, which is which has this additional calculation possibilities, and now micro omegas is actually equipped with all these different kinds of possibilities, like you can have the 2-component dark matter, you can have extended dark sector with co-annihilation effects and all that, which was not there earlier, but nowadays it's more sophisticated, and here you can do those kind of calculations, and of course then you can merge them together to do whatever analysis, this parameter space scans. The numerical routine that you have to run over different set of parameters, that you have to write that kind of code, whatever Python or etc. But you can call them in loop or something, and then you can generate your parameter space scans, which is compatible with your dark matter searches, collider search prospects, and so on. So this is a rough sketch of what usually people do. And as I said, that I will give you a quick introduction to fine rules, and it's basically a Mathematica based packages, and it generates output as we just discussed for MATGraph, FineArts, Calcade, etc. And what one needs to do, that this fine rules automatically embed standard model, and it has many effective operators also. So I will give you some examples as I go along, and how do they look like, and etc. So so these are the files that you usually have in the fine rules, and there are some files which are like Cabibo, diagonal CKM, massless. These are .rst are the restriction files, which basically says that these are better not to touch. The files that we usually have to modify, or rather if you want your new interactions to be embedded, is this .fr file. Okay, so this is the model file that we will mostly talk about, and then there is this implementation notebook, which is the standard mathematics notebook. It's called sm.nb, and smqcd-nlo is the additional file used for generating UV and IR, I think, counter terms. R2, okay, okay. So what is there in the standard model file, say for example sm.fr. Now you can imagine that these are the basic informations that you have to have. Well, I mean the model information, the index definitions, which is basically the preamble, if you can say. Then you have to have the declaration of the fields, name of the particles, spins, PDG codes. This is something interesting, that these PDG codes of the particles are already decided for the standard model particles and also for supersymmetric particles. But if you have, so for example, you want to embed a vector-like fermion and you want to study its prospect, then you have to devise a PDG code that doesn't match with those ones, and then and of course you have to define their indices, quantum numbers, the masses, widths, classes, and etc. And then you also have to declare the gauge group, like it's abelian or not, representation matrices, the structure constants, the coupling constants, gauge boson or vector superfields, etc. And then of course the parameters that go into the Lagrangian. You can devise it in two ways, like you have the external ones that are the independent inputs that you want to give, and the internal ones will be the ones that will depend on those external ones. So this is basically the content of this .fr file that you need to be you need to work upon, and finally all this constitutes the Lagrangian as a whole. Okay, so yeah, this is the first part, which is the preamble, that you do this model name. Say for example, this is standard model, and then you have the information like here, for example, these guys are the ones who wrote it, and then version, date, etc., etc. This is something which is optional, as you can understand. And this is the part which actually talks about the standard model gauge group. Now, we all know the field strength tensors in standard model, like B mu nu is del mu B nu minus del nu B mu, W mu nu is the SU2 field strength tensor, which has another additional index I, and this is actually having this additional term because of the non-abelian gauge group, and this is for the SU3, this is for the gluon field, and once again these are the structure constants associated with SU2 and SU3. Yeah. So here, for example, you first define the gauge boson associated with this U1Y. So this is abelian, that it's true. Coupling constant is defined as G1. The gauge boson is named as B. The charge is Y, which is the hypercharge that you remember we talked about. Now you do it for SU2L, and this is not abelian, so that is false. The coupling constant is defined like this. Gauge bosons are defined like Wi. The structure constant is epsilon, so this is defined. And these representations are Ta, Sud. The Ta, A, B, C, these are essentially the generators of the SU2, which are Pauli sigma. This is I think already defined in it. And then you have this f of SU2L ijk, which is I epsilon. So this is, I think, the commutation relation, right? So which is I epsilon ijk, which defines the structure constant associated with this thing. So for SU3, once again, I mean, it's a similar thing, and usually what happens that we do not unfold the SU3C part, because particularly if we are interested in embedding SU2 interactions or electroic extension of the standard model, which we mostly are doing. So that I will come to the next slide actually. But this is the part which therefore is most important for us. And yeah. Okay. Yeah, now this part is interesting because you have basically unfolding this. There are two nomenclatures you see. This is SU2W and this is SU2D, and you see that SU2W has a range 3, whereas SU2D has range 2, and this you can understand that there are two representations of SU2, one which is the adjoint representation in which the gauge bosons transform, and the other is actually the fundamental representation in which the particles, the doublets actually transform. So this SU2D will refer to actually the transformations of the quarks and the lepton doublets, whereas for SU2W, it will be the corresponding gauge bosons. Okay? So this is what you do, and as I said that we usually do not unfold the gluon and color indices. So this is usually the no unfold once again, but you have those possibilities, like you have both the representations, the adjoint and fundamental representations associated with SU3 for triplet and 8 gluons which are followed from the adjoint representation of the SU3. And here are the indices which are defined corresponding to each of these, because when you expand them, you know, for example, for SU2W, there will be 3 sort of vector bosons which will be defined like Wj, where j will run from 1 to 3, and then for SU2D, the index will be k, and that will run between 1 to 2. For gluons, A will run from 1 to 8, for color M will run from 1 to 3, and then there are generation indices or flavor indices, whatever they are. However, while we are writing the interaction terms in the Lagrangian, we better be consistent with these indices that we define here. Now there is another important point which is actually about the interaction hierarchy. So basically this shows the priority, like QCD, whenever that is there, it will actually be the dominant one, and QED will be the subdominant one or will be neglected, and this is usually the M dollar interaction hierarchy, interaction order hierarchy that we have. And whenever you have new physics in it, because you want to prioritize it, the way that we do is usually we put the new physics comma 1. I think this, if you put new physics comma 2, I think it can get neglected, right?
It depends how you write in that graph. So if you explicitly mention that you want this, then it will be taken. But if you
don't mention, then this dominant contribution will only be taken. Yeah, vertices will be generated for all the cases, but it's the priority that you decide. Yeah. So yeah, this is the part which is important for us, which will embed the cases for BSM, EFT, etc. Okay, now these are the particles which are already defined within the fine rules, and these are something that we have came across, that the fermion fields, you can have two different representation. One representation by which we write the standard model, which we have all talked about, like left-handed lepton doublet, right-handed singlet, right-handed lepton singlet, left-handed quark doublet, right-handed quark singlets. On the other hand, you can have this physical fields defined by UQ, where UQ defines UCT with their electromagnetic charges, DQ defines the down type quarks with their electromagnetic charges, but this notation like UQ includes U, C and T, DQ includes D, S, B, L includes electron, muon and tau, and nu L actually defines all these 3 flavors of neutrinos, nu E, nu mu and nu tau. Then there are vector bosons, and once again you can have them in the unphysical way, which the way that you actually insert them in the standard model Lagrangian, like Wi and Bi, and then the physical basis of the gauge bosons like the photon, Z, W and gluon. And similarly, you can have the scalar bosons the way that we have, that this is the unphysical isodoublet, and these are the physical fields like the Higgs, Goldstones, G0 and GP, referring to these 2 Goldstone degrees of freedom. And then there are ghost fields here, which show up, but the point is depending on which gauge that you actually want to work upon, these ghosts and goldstone fields can become important or not. We know, for example, if you are working in unitary gauge, the interactions with the ghosts and goldstones becomes unimportant. But if you are working in what is called Feynman gauge, then this actually will play a part. So, yeah. Yeah, there is a kind of ignorance about these fields because most often, while we do theoretical calculations, we work in unitary gauge. But please remember that if you are not using unitary gauge, this is very important and we should take care of this part. Now, let's talk about the fermion fields. So, this is the class name. So, this is the one which defines the physical fermions, like for example, L, which has this electron, muons and taus in it. And the indices will have the generation index, as you can understand that it will have 3 generations like electron, mu's and taus. And these are not self-conjugate for sure. You have to define their masses like mass of electron, muon, tau, so on. You assume the decay width to be 0. I think you can, if you wish, you can include the decay widths of muon and tau if you want. Then the quantum numbers, because these are the physical fields, so here there are 2 quantum numbers that we actually associate. One is the electromagnetic charge and one is the lepton number. Okay, so quantum number is therefore electromagnetic charge -1 and the lepton number is 1, and there are propagator levels that you can set, propagator type, you know, the usual way that we draw the Feynman graphs associated with the fermions, like straight with an arrow forward, and these are the standard PDG code for electron, muon and tau. And then there are these particle names that you assign, and then there are these corresponding antiparticles and the full name. So, this completes the definition of L. Similarly, you can imagine, you can define this class for the physical quarks, right, for Q, and which will include, you know, QU like up, charm and top, and similarly for the bottom one, etc. Now, this is the one which is the unphysical one, but importantly, this goes into the definition of the standard model Lagrangian, because this is exactly where you define them like the left-handed doublet. So, once again, the class name is LL, as I just mentioned, and these are unphysical, which is true. Indices, now here you see that this index is coming into play. You remember that SU2 has 2 different representations. SU2W was the adjoint one and SU2D is the fundamental representation. So, here the index will be SU2D, and there will be of course the generation indices, and the flavor index is associated with this SU2D. These are not self-conjugate, and we remember that in order to be consistent with the standard model, Q is equal to -1 associated with the electrons, and for neutrinos equal to 0, we had this Q is equal to T3 plus Y. So, the hypercharge associated with the doublets was actually Y equal to -half. Now, say for example, you want to define a new vector like fermion doublet. Okay? So, what will be the change? You associate what kind of vector like doublet that you want to add to the story, you define a name, and you have to use this index SU2D, you have to define your corresponding hypercharge with which you want to define that additional vector like doublet. The one important point here is to note that here the components that constitutes this left-handed doublet are having left-handed projections. So, therefore, that is how you have this included in it, like PL multiplying each of this component, and that is what this project M. This project M is actually the PL operator, which is half into 1 minus gamma phi. Okay? And this will have to be embedded explicitly in this particular way. And this is basically the, you know, matrix multiplication, if you may say. Okay? And the same happens. So, this SP1 1 is the component up, SP1 2 is the component which is down, and that both has to be explicitly multiplied by this PL, which is defined by project, I mean whatever that you say, proj m or whatever. Now, so this was the case of left-handed doublets. What about the right-handed singlets? The right-handed singlets are like LR, and in this, of course, you have to have, because they do not have any isospin, so the quantum number of electromagnetic charge is essentially fed from this hypercharge only. So y is equal to -1, and the definition is simply LR sp1 ff, and here you see that it is not a matrix, unlike this LL case. It's a singlet, so therefore the only entry is project P sp1 sp2, and this is the usual multiplication for each of these components. So this is like ER is equal to PR into E. So this is basically the definition by which you can do. So this goes for all the cases, you know, for the quarks also. Okay, it's okay, makes sense. Now let's come to the case of vector boson, and so once again you do this mass, width, particle name, quantum numbers, PTG code, etc., 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 and these are the physical ones, and then there are these unphysical ones actually which enters into the standard model. Now here you see that we are defining this B mu in terms of the physical ones. So Z mu minus sin theta w Z mu plus cos theta w A mu, the relation that you have already come across. So similarly, this is for the you know, hypercharge field, and this is for the Wi, and here you will have to have this index Su2w. Once again, I would like to remind you, there are two representations. This Wi are transforming under the adjoint representation of Su2. So the index will be associated with Su2w, and then you have this Wi1, Wi2 and Wi3, and we are defining them in terms of the physical W's, like W plus W, you know, W1 plus IW2 by square root of 2 and so on. Okay, and W3 is the one which is cos theta wz mu plus sin theta w mu. So this completes the definition of the vector boson. So now you can define the scalar boson exactly in the similar way, and the indices will actually involve the transformation of the Higgs doublet under the fundamental representation of Su2. So therefore that is what is here. You have to define its hypercharge. We all argued that the usual way that we write the standard model Higgs doublet has this hypercharge of half, and the definition is that you now explicitly write that this is the Goldstone in the charge associated with the phi 1 plus I phi 2. If you remember in the definition of the Higgs doublet, this is what is the GP, and then this is the physical part which is actually there, which we all write in terms of unitary gauge, but there is this additional piece like IG0 associated with phi 4 field, which is the another Goldstone degrees of freedom. So this is explicitly a definition, and here define depending on whether the Feynman gauge is true or false, the Goldstones can be turned on or off. Now you come to the parameters. This part is not very difficult. The thing is, you define this alpha s at mz, and which is actually Ga square by 4 pi. So this has a QCD of QCD degree of order 2, if you may say, or QCD order of 2. And this is the one that you define, that alpha s mz with its value. So therefore the internal parameter correspondingly will be this Gs, which actually enters into the Lagrangian once more, and the interaction order will be QCD1. Okay, and you can define the parameter name, etc., etc., etc. So it is defined as square root of 4 pi alpha s, where alpha s you have defined as an external parameter, therefore the Gs is an internal parameter. Now with all these ingredients, you are there to write the Lagrangian. So this is the generic form, that you have a block, then you have all the indices with your piece of Lagrangian actually have, then you expand indices and then you write the Lagrangian, flavor expand, the flavor this thing, and if there are some conditions, I will come to this point when we actually write at least some part of the Lagrangians. I will explain what kind of conditions that you may mention here. So yeah, in this flavor part you have basically the SU2W and SU2D cases, I mean both the fundamental and adjoint cases, and these conditions include this possibility of using Feynman gauge or not. And these indices will have all kinds of indices, like you remember for fermions you have a spinor index, Lorentz index is there, I mean for all these vector boson fields, also with the gamma mu's which actually go in. Then there are cases of doublets which you have this indices II, JJ, KK, the color indices are AA, the flavor indices are FF, and remember these indices, the notations of these indices have also been defined at the very beginning of writing down what kind of indices that you want to assign for each of these different properties, and it is usually the customary that we do not sort of mix and match, because then the Lagrangian will be not complete. So the total Lagrangian is of course in the standard model Lagrangian, the gauge Lagrangian, the fermions, the Higgses, the Yukawas and the ghost terms. So for example, let us look into the gauge part of the standard model Lagrangian, which we all know that it has this QCD part, this is the SU2 part, SU2L part, and these are the U1Y hypercharge field strength tensor associated with this thing. So let us say for example look into this thing, and this as I said that this is this block. What are the indices? You have the Lorentz indices mu nu, II was the indices associated with this SU2W, so that is there, and AA is the index corresponding to this color index, also in the adjoint representation, and then you expand indices writing -1/4 Fs B mu nu, Fs B mu nu, and in general this Fs is essentially defining the field strength tensor. So the generic notation is field Lorentz index 1, Lorentz index 2. So this is the way that you can do, and this is exactly what it is. So you have this thing, and then you have to flavor expand in terms of SU2W. You can do this expansion for the SU3C case also, but that will unnecessarily make things complicated and not required for the purpose that we are actually going to look into. Any questions here? Okay. So now let us come to the fermion part of the Lagrangian. So we know these are the kinetic terms which are there for the left-handed doublets, for the right-handed singlets, okay, and so therefore once again this involves the index.
Sir,
yeah,
I have a question.
Yeah.
That in the beginning you showed 3 restriction files. One of them was the mass restriction. So if I work with a model where I need to have some massless particle which are already there in massless condition, they are considered in the file some particles are considered as massless. So you told that we should not touch the files.
No, I mean yeah, I mean yeah, you asked the question.
So suppose I am working with a model and in a particular scattering I want to observe. So there I need that a particular particle to be massive. So can I change there in the?
I think you can. I mean, it's quite possible. I mean, it's not something very difficult. Usually, there are light quarks and light electrons, leptons there in the massless. I mean, but changing them to be massive is not something very difficult. Yeah, you can.
And the that hierarchy part, their QCD, QED and new physics. So in the parameters we have to write that thing, that QCD in the order block, QCD comma 1 or something. So if I write for the BSM particles or some new particles, that new physics comma that order or something, will that understand that it is, I mean,
yeah,
the meaning?
I think it works fine with this new physics comma 1. I mean, because it automatically then prioritizes that you have to take into account the new physics contributions. If you put as Shankho mentioned, because he is more expert in this part. So if you put new physics comma 2, then depending on in MATLAB in particular, that if you want to, it may or may not take into account this higher dimensional operator contributions in that particular case. So therefore, it is important that you keep the new physics preference as equivalent to the QCD, so that that is taken into account.
Also, we are defining the indices at the beginning.
Exactly.
And while writing the Lagrangian part wise, can we redefine or rename the indices in the local
You
scope?
can do, but then you have to unnecessarily change the whole standard model Lagrangian. So my idea is to not to kind of fiddle with the standard model Lagrangian too much, but include those operators, higher dimensional effective operators, or the new physics that you want to address based on the kind of like SU2W index, SU2D index, SU3W, SU3D, etc. So these are already defined like II, JJ, KK, etc. Flavor indices are FF. If you fiddle with that, then you have to be first of all consistent, because the whole standard model Lagrangian you have to change. Secondly, it doesn't serve the purpose. You can do it consistently. I mean, it's not a very difficult job. It's just a little tedious that you have to rewrite the standard model, and then you can sort of write whatever. Then you say, for example, you want to introduce a vector-like doublet. Right-handed neutrino to be inserted in your model, right? So then you have to, right-handed neutrino is okay because it's a singlet under the standard model. It will only have the flavor index. But for example, if you want to include a vector-like lepton doublet for some reason, then it is easier that you stick to the indices notation which is defined in the standard model, and you just rename the particles which enter into the doublet. So as I said that for instead of writing that LL, you can follow exactly the same block. You can write a block without having those projection operators embedded to define them. So that will do your job. If you want to include a triplet, say for example, you can do exactly in the same way, because you also have this adjoint representation and you have that indices over there. So you can do that. You want a Higgs quadruplet. You can follow the Higgs doublet pattern and then just use the flavor indices to expand how you want your matrix to be. The definition of matrices are also there, so you can use that purpose. So changing the flavor indices is not a good idea, because unless you are having a new gauge group. So for example, you want to extend your model with a new gauge group like an additional U1x. Then of course you have to devise a new index associated with that. But otherwise it is easier. If you want particles to be transforming under the standard model gauge group, I will come to the case of Z2 symmetry later, which is often required for embedding dark matter particles into it. But otherwise changing indices do not help much. Yeah, but changing the mass is trivial. But changing the CKM and PMNS is a little more complicated. I think because there are restrictions, you know what are the experimental numbers and etc.
Yeah. Thank you.
Yeah, so this is the part which does the case for, so you see this QL bar, gamma mu, DC of QL mu, etc. And then you have for LL, UR, DR, etc. And this flavor expansion has to be done both in SU2W and SU2D. And here there is a restriction that this VCKM IJ, VCKM JK dagger equal to delta IK. This is something that we have to assign to this fermionic Lagrangian. Then of course there is another part. There are two parts essentially. One is the Higgs part. I mean, once again, here the one part which is important is actually this Feynman gauge rules, because if not Feynman gauge, then these goldstones actually go to 0. So this is the part which is interesting in that particular context, and the rest is essentially very, very similar to what we have defined. You define plus mu h square, phi bar phi, etc., lambda phi dagger phi, phi, then you have the flavor expansion exactly the way that we wanted to do. And then the last part is the standard model Yukawa Lagrangian, and it is once again, it's not very difficult to kind of find. The only thing is that which we didn't write explicitly in our first lecture was the presence of this, I mean, we wrote this Yukawa matrices, but you all know that these have this additional CKM elements entering into it. So, which actually comes here. If you see that the corresponding YD FF2 FF3, then says CKM FF1 FF2, then QL bar FF1, and this dr ff3, and then you have the phi 2. So this is a consistent matrix multiplication, nothing more than that, which takes into account this indices ij here, and however you also have to remember this is a doublet, so that index goes in, and the spinor indices are associated here with this QL bar and also with the dr. So but this you have anyway defined before, so it will not be very difficult for you to kind of associate with each of these term, and the flavor expansion here will only be SU2D. And once again you have the same condition that this VCKM dagger VCKM will be equal to 1. The SU3 part, see the point is, SU3 part of the Lagrangian, I mean we can expand, but I don't think it is going to give you, I mean it depends on your choice. So for example, if you want to embed, suppose supersymmetry in your model, which has this SU3 particles, I mean particles transforming under QCD gauge group also, there you require. But the purpose that we are doing, which is an extension of the electroweak physics, we don't require it. So that's my statement. You don't fiddle with that. Yeah, exactly. If you want to do that, vector-like quarks, Sanjay, right? So in that particular case, if you want to do that, then you have to kind of expand that part also. So yeah. So, but if you just have the electroweak extension of the Lagrangian, we are good enough to go with this part. So now is the most interesting thing. So let us try to address this SMEFT operators. There are 3 examples which are shown here, and instead of going painstakingly through each of these cases, let me kind of take one example, and we can see how exactly they can be added to the standard model Lagrangian, and that will do the job. So for example, let's say this Higgs current operator, which looks like phi dagger I d mu phi, where there is this 2 arrows on the d mu, which basically means that phi dagger I d mu double arrow phi is essentially phi dagger I d mu phi minus I d mu phi whole dagger phi. So this is what it is. And also the sigma mu nu, all of you know that this is I by 2 gamma nu commutator, okay. So this has to be explicitly mentioned because they do not know the definition of d mu this thing, and they do not also know sigma mu nu, but gamma mu, all these are there within within it, okay. So yeah, now this is I mean, in order to do this, you have to basically define first the parameters. So what are the parameters? You are assuming here for simplicity that there is only one new physics scale lambda, and then there are 3 different Wilson coefficients. I mean, when you are including all the 3 operators, say for example, together. So these are the CW, CHQ1, CLEQ3, and so these are easy to understand. These have interaction order NP, 1, which she wanted to clarify. So for all of these cases, you have this interaction order NP, 1. For lambda, this new physics scale, this is for some reason. So for example, here you assign the value 0, but that is just, I mean, you can assign any value that you want. And here the warning that Jose actually gave to you may come into play. like if you are inserting operators which are involving gauge field strength tensors, if you assume weakly coupled and decoupling new physics, then they might come at the loop level only. And so here in the value, instead of quoting 0.1 or something, you have to include that 1 by 16 pi square explicitly if you want. Okay, so this is, you can also put that in the Lagrangian separately. You can put it here also. If you are varying the parameter, wherever it is easier for you, you can do that. The one thing that I wanted to draw your attention to, that this lambda, which is, say for example here 1 TeV, this has unit of mass, and so therefore the interaction order is written like QED minus 1. So this is one part. So for the dimensionless new physics couplings, that is actually new physics comma 1, but for mass parameter like lambda here, that has a unit of mass, and so that is written like QED minus 1. Why this is actually done, I don't know. I also don't know. Shankho? I mean, this is funny, but this is how it is. Yeah, QED minus 1 sounds a little funny, but it says that if you want to include the dimension full parameters, whether it's 1 by lambda square, lambda cube, that will automatically be taken care of when you write the Lagrangian. But while defining the lambda, it's
how they define the Vertex factor, suppose E, electromagnetic constant, so that depends on that.
yeah. So I think Deepankar is absolutely right. Yeah.
Also they have
order for wave also. Yeah, but I mean, so this is because I think his answer is in a sense that it is because C by lambda is coming in the vertex factor. So that's how this is QED minus 1. Yeah. Okay, all right. So this is the operator which I was telling you, that we have this C1 HQ lambda square phi dagger I d mu phi QL bar gamma mu QL. So what you can do, that you can define these two parts separately, like phi dagger I d mu phi is this part where you have to include the Higgs doublet. So therefore the same point arises, Feynman gauge rules, if not Feynman gauge, blah blah blah, expand indices in terms of, so there are only this indices associated with SU2D, and then you have you define this phi dagger I d mu phi as we just wrote in the last slide, and this is this DC, you remember, is the covariant derivative associated with each field, which is defined. So DC of phi is already defined. So therefore you can simply take that and just put the indices, the SU2 index and the mu index, which is the Lorentz index, and you define explicitly. And so this is this part. Okay, and then you have QL bar gamma mu QL, that is easy. So you have this QL bar and this QL, this is the gamma mu, and you must have to make sure that this matrix multiplication is correct, and that's it. And in both cases you flavor expand in terms of SU2D and SU2 this thing. So then you say that, okay, so all right, actually this has explicitly this part, I must say that this is explicitly this part multiplied with this HDH mu, which we defined as for this one. Now this is a nomenclature which is up to you. You can call it anything. HDH is something that is that we wanted to define it, but you can define it in any different way. So this is explicitly this part multiplied with this part, which is defined here with this prefactors somewhere sitting. Yeah, this is here. So this is SL, this is this thing, that this guy with this guy by lambda SMEFT whole square. So this does the job for you. Now I do not want to go over for the cases here, so the slides will be there with you, so you can actually look into. Now Now let's come to this part, that suppose you want to add any dark matter operator. I beg your pardon for this typo. These are not the dual fields that we are inserting. I mean, this is W mu nu only. So with, say for example, zeta square. So this guy, this zeta is now the dark matter. So we are defining an effective interaction between a scalar dark matter with the field strength tensors of the standard model, say for example. Now if I had to do this, what additional thing that you need to do that you didn't do in the previous exercise? The first thing is that this new dark matter field is not defined in your Lagrangian. When you are defining the standard model Lagrangian or writing the effective operators with the standard model fields, all the fields are defined. So you just have to define the operator using them. But when you are doing the dark matter case, then first thing that you have to do is to define the dark matter. So for example, here you want to have this to be a scalar dark matter. Now you give a name, you define the mass, it doesn't decay, so it's 0, there is a propagator level, etc. PDG code, you put something arbitrarily large, and so that there is a less chance to get conflicted with the existing one. There is an interesting point which I must draw your attention to, is that in the particle name you must define the dark matter with a tilde, whatever, tilde A, tilde B. Why this tilde? This makes sure that you will only generate vertices which are protected by the Z2 symmetry of the Lagrangian. Okay? So this tilde ensures that, because otherwise you have to define the Z2 symmetry explicitly or something. So this is the easiest way that you can make sure that this doesn't have a special symmetry or a special charge which other standard model particles don't have. So similarly, for the scalar, the way that you have done, for the fermion you can also do a dark sector doublet, right? So this is a dark sector scalar singlet, this is also a dark sector fermion singlet, but you are not happy. You wanted to have an extended dark sector. You wanted to insert, like Sanjay wants, to insert a doublet of the vector-like quarks, which is protected, say for example, by Z2 symmetry. You can do that. But you have to then define exactly similar to the LL case, but with the tilde as their inputs for each of these fields that go inside this thing. So this symbol allows the packages like micro omegas to identify the dark matter candidates. So if you don't do that, then they will get confused. And this part is trivial, which I just talked about, and this part is also not very difficult because we have defined this Fs B mu nu, once again ignored the tildes here, and then this xi square, the flavor expand is SU2W and SU2D, and so on and so forth. So this is how exactly it goes. There is a special interest for which we wanted to write these operators of this particular kind. That physics is very interesting, but perhaps it is not time to talk about that kind of a physics, because this generates actually a kind of dark matter interaction where the monophoton missing energy distribution is completely different from that of the standard model background which is produced by the neutrinos. So therefore, it is kind of interesting for that reason. But then finally, whatever operators that you have already inserted, you have to add them all together. And then you basically have to do the implementation via this Mathematica notebook, and you do operations as follows. You can load the model, this is a very important check, that you can check the hermiticity of the Lagrangian that you have inserted, and if everything is fine, it will actually generate all the Feynman rules for you. Now these are complicated to look into, but we all have Cheng and Lee or any quantum field theory book that you write. So there you can explicitly check whether the Feynman rules that you are generating using this package is okay or not. So these are all the standard model ones, and then you have these additional pieces for the SMEFT. For example, this vertex HHZUU, which is coming from one of these operators that we inserted, that is actually here. Okay. So, if you are doing an analytical calculation, you can also check the consistency of this using the analytical calculation. And similarly for the DMEFT case, you can check this is chi AZ interaction that you are generating, and there is a fine the corresponding rule is here. Yeah. So then the part which we couldn't talk about, that then there are options in the fine rules that you can generate the files which are compatible with incorporating in MATgraph, which are called this. So these are the commands, for example, write CHO output. This will help you to feed the model into micromegas and do your relic density and direct search calculations. This will allow you to feed the right UFO files. So these are the files which are usually fed into MATgraph, and they will do all kinds of collider simulations for you. You can also feed this into fine arts, and this is the command by which you can actually do that. So with this, I think I will end. So this is basically, so this file will be there with you. We are going to provide you an explicitly zip file with this actual SMEFT and DMEFT operators imported there. What you have to do, that you have to install Mathematica, you have to install the fine rule package and run those files to see exactly whether we are consistent, and you can do a phenomenology. So that we will do via email. So no, not here. Yeah. Okay. If they can do it here, I have no issues. But yeah. Okay. So with that, I will stop. So there are a lot of other things which one could have talked about, like the implementation and how one can do the MATgraph calculations. But yeah. Okay. All right. With this, I stop. Thank you. Oh, okay. So, okay. So, if there are questions first, let's take if there are questions. Yeah, so the urge is that use those zip files that we are providing you, where these SMEFT operators are embedded. You do implement them in your fine rules, run them, and see if you are getting consistent answers. And then you do your next exercise, like whether you want to do collider calculations using MATgraph, or you want to go through the dark matter calculations using micromegas, whatever that you want. So, but unless you do that, it will not be yours. Yeah. Any questions? Yeah.
So while mentioning the model information at the beginning, we have to mention the interaction order, and in that we have to write QED1, QCD1. So I've often found like error with those orders. So when we include any new physics particle, so what does that imply? And if we want to include in new physics, so sometimes I have written like NP1 and then it works, sometimes it doesn't work. So how?
Yeah, usually NP1 does work. I mean, when you write NP, 1, then it takes into account the new physics interactions that, or the vertices that you generate. The problem is that suppose you want to do a calculation like E plus E minus to ZH, or PP going to ZH, as Shankhu was talking about. Now you have this operator that we have included this within, and you defined NP, 2. Then there is a possibility that it will not take. So then you know that we saw that there is a contact term like QQZH, which should actually contribute or interfere with the standard model graph, right? Yes. So the point is, if you define NP, 2, there is a possibility that it may neglect it while doing the collider computations. So that's the worry. So because we do want our new physics to come in, or the effective operator contributions to play part with the standard model contribution, so it is always good to keep the new physics to be NP, 1. So then there is no chance in missing. But Shankho, is there any further comment that you want to add?
That's all.
Yeah.
You can generate, let's say, when you
Yeah. Anupam, can you talk over the microphone?
You can generate AB going to CD
Right.
with NP equal to 4. That means up to all NP equal to 4, all vertices, all diagrams it will take care.
Okay.
You have to write explicitly in mat graph. Like if you
Right.
do not give it the proper hierarchy, then you have to mention it while writing your mat graph process that you need these many new physics vertices, then it will consider.
Yeah, so as they mention actually, so it also is thereafter when you actually put it in the mat graph and then want to do the computation. So if you explicitly write or emphasize that I want this new physics vertices to appear at least this order, so then it will take care in immaterial of whether you write np comma 1 or np comma 2 in the
Sometimes the error is because you define two parameters with NP1 and then
Ah.
find the Lagrangian, you put some division between the two two parameters. Like if you define lambda is equal to NP1 and also C is equal to NP1, so if you write C by lambda, it becomes order X.
Okay. So the confusion may arise by defining this C by lambda. I mean, which is np comma 1 and which is QED comma minus 1.
Not QD. If you define NP1 for lambda also,
Acha.
the NP1 cancels out, so it becomes order.
No, I understand. So that's the point, that if you define both with np1, then there might be an issue. So that's why, I mean, this lambda you define like QED comma minus 1, while for all the Wilson coefficients that you are defining is np comma 1. So that might be the useful way. More questions?
So someone asked at the beginning whether what to do with this restriction file about if we don't want electrons to have masses and so on. So it depends on whether we want to use the restriction file at all. So like while running the Mathematica notebook, we can decide not to use that restriction file altogether. In that case, all the masses will be taken into consideration. If we put that restriction file, then some of the masses or widths will be taken to 0, and then we can also modify the restriction file according to our
Choices.
needs.
Yeah. Okay. So, okay, thank you.